So in this video, we're going to talk about how we use the cofactors to find a new matrix that we refer to as the adjoint, and how we use the adjoint to find the determinant of a matrix. So before we get to defining what the adjoint is, we need to talk about what a minor of a matrix is. So the ij minor of an n by n matrix, which we're going to denote m sub ij, is the n minus 1 by n minus 1 matrix formed by deleting the ith row and the jth column. So, for example, if we have the matrix A, which is just, I have the integers 1 through 9 in a 3 by 3 matrix, let's consider the 1, 3 minor. So that, again, we will remove row 1 and column 3, and that leaves us with this submatrix 4, 5, 7, 8. So that's the 1, 3 minor. If we wanted the 2, 1 minor, again, we would eliminate row 2 and column 1. That leaves us with the matrix 2, 3, 8, 9. Notice that we've done this already when we've talked about finding determinants with cofactor expansion. So minors are related to cofactors. So just to remind us again what a cofactor is. So the ij cofactor of an n by n matrix, denoted C sub ij, is equal to this negative 1 to the I plus j times the determinant of the associated minor. So notice that this negative 1 to the I plus j essentially is our sign board that we talked about back when we were doing expansion by minors with the determinant in the last video. So again, as an example, using the same matrix, C1, 3, the 1, 3 cofactor, we put 1 plus 3 up in the exponent, so we have negative 1 to the 4th, essentially, in the determinant of the associated minor. Notice this is exactly what we would do if we were trying to figure out the cofactor expansion, or the expansion by minors, for the determinant. We would go to the sign board, and if we went to the sideboard, the 1, 3 entry, the plus minus entry in that sign board would be a plus there, and that's exactly what we have here. So we get a 1 times the determinant of that, and if we go calculate the determinant, we get negative 3. Likewise, if we look at the 2, 1 cofactor, put 2 plus 1 up in our exponent, that just makes a negative coefficient out in front of our determinant, and go through and calculate and get 6. Again, we've done computations like this in the previous video when we were talking about doing determinants by expansion by minors. So now we're ready to make the adjoint. So the adjoint of a matrix A has to do with these cofactors. And the way we form the adjoint, the ij entry for the adjoint is the ji cofactor. So what we mean is that, for example, if I were going to put the 1, 3 cofactor in, it would go in the 3, 1 spot. We flip around the rows and the columns for the cofactors, and we'll see why we want to do that in a minute. All right, so let's do the adjoint. So here is B. I should have brackets rather than vertical bars because this is a matrix, not doing a determinant. But here's our matrix B. Let's calculate the cofactors. Let's do the first one here. So the 1, 1 cofactor, again, we eliminate row 1 and column 1 to get the minor. Take the determinant. And this, I'm using the formula for the cofactor, but again, this is just sign board. We did the 1, 1 cofactor, sign board would be a plus there. So if we put 1 plus 1, and we get a positive 1. Take our determinant, we get negative 16. Do the next one. Row 1, column 2 gets deleted. So we're left with 1, 2, 9, negative 3 is the minor. Take its determinant. The row 1, column 2 has a negative associated with it on the sign board, or again, you can use the formula. We get 21. And we do the rest for the other cofactors. We see that the 1, 3 cofactor is 8. The 2, 1 cofactor is 2, and so on down the line. So just clicking through the rest of these to show you what they are. There are our 9 cofactors associated with this matrix. Now again, to form the adjoint, we flip rows and columns. So this C1, C11, C12, C13 is going to be the first column in the adjoint. C21, C22, C23 will be the second column in the adjoint, and so on. So we see negative 16, 21, 8 down the first column. That was the first row of cofactors. 2, negative 15, negative 34 is the second column in the adjoint. That was the second row of cofactors. Negative 4, negative 3, 2 is our third column in the adjoint. That was our third row of cofactors. That's how you form an adjoint. So let's talk about why we care about the adjoint. So let's say I identify A as its row vectors. So the notation is a little funky, but all the stars here mean is that these second subscripts go across the column. So A sub 1 is just the first row, A sub 2 is the second row, and so on down the line. The associated adjoint then would be find the associated cofactors for each of these, but write them as columns. So this C sub 1 star means that these are the cofactors written as a column for all of the entries that go across the first row. And then likewise, we do the same thing for the second column, ith column, jth column, nth column. All right, we're going to compute the product of A times its adjoint. Well, again, when we do the product, remember we line up row with column. Well, if I take the entries in row 1 and multiply them by the cofactors in column 1 in the adjoint and add them, we get exactly the determinants. That's how we calculated determinants when we did expansion by minors, right? We took that entry, multiplied it by the first cofactor, take the second entry, multiply by the second cofactor, and so on down the line. So anytime that the subscripts match, when I take row 1, column 1, I get determinant of A. If I take row 2, column 2, I get determinant of A, because we talked about how we can expand along any row we want and get the determinant. So anytime that the subscripts are the same here, I get determinant of A. So that means when I take this product down the diagonal, we're going to see determinant of A, because that's exactly when the subscripts are equal. All right, so what happens when the subscripts are not equal? Well, let's take a look. Here's a new matrix I'm forming, but it's identical to A, except that we've replaced the jth row with the ith row of A. So we have repeated rows here. Ith row is A sub I. The jth row is also A sub I. Here's our adjoint again of A. Now, what happens here if I want to take the determinant of A prime? Well, the determinant of A prime, of course, is going to be 0. Because when I take the determinant, I've got two identical rows, and we know that anytime we have identical rows in a matrix, we have a determinant that's equal to 0. All right, but now we can also calculate the determinant of A by expanding along the jth row. If we expand along the jth row, notice that we eliminate the jth row. The rest of this is identical to A, which means that the jth set of cofactors here is the same as the same set of cofactors for A as they are for A prime. Because again, remember when we make the cofactors, we delete the row we're interested in. The rest of the rows for A prime are identical to A. So, we get that the determinant of A prime is 0. To take the determinant of A prime, I expand along the jth row and multiply by the jth column over here. Do that dot product idea, but remember the jth row of A prime is the same as the ith row of A. That means that dot product is 0. So what that's telling us is that anytime that the subscripts are not equal, we get 0. So we said in the previous slide that when the subscripts are equal, we got determinant of A down the diagonal. Everywhere else is a 0. That means it's a diagonal matrix, and in particular, every entry on the diagonal is determinant of A. So in other words, if I take A times the adjoint of A, I have the identity matrix multiplied by the scalar determinant of A. Better yet, if A is invertible, I now have another way that I can calculate the inverse. If the A is invertible, remember that determinant is 0 or is non-zero, so I can divide by it, and I can also multiply both sides by A inverse, and we get this formula now for the inverse of A in terms of 1 over the determinant times the adjoint of A. So let's see if we can do an inverse using this formula now. So let's say we have the matrix D. It's there. First thing I need to know is its determinant. So expand along the second row because I got zeros in there. Use my 2 as my coefficient. I know it's in the negative spot, so it's negative 2 times the associated determinant of the minor. And calculate that, we get negative 30. All right, so we have the determinant. The next thing we need is the adjoint. To do the adjoint, we need the cofactor. So just to click through here to give you the adjoint. Along the first row, these are the associated cofactors. Along the second row, these are the associated cofactors. And along the third row, these are the associated cofactors. Now again, remember when we make the adjoint, the associated cofactors from the row go down the columns. So the adjoint of D here, down the first column is -2, -4, 0. Those are the cofactors from the first row. They go down the first column. -39, -3, -15. That's the cofactors associated with the second row. 12, -6, 0. Those are the cofactors associated with the third row. Now we're ready to get the inverse from the formula from the previous slide. 1 over the determinant, so 1 over 30. There should be -30. I missed a negative sign out here. I apologize. 1 over -1 over 30. So all these signs in here on this last part should be flipped. They should have a negative here times this matrix equals this one over here. All of these signs should be opposite. So everywhere you see a negative here, you should have a positive, and then that one should be a negative. I apologize for the typo. But you get the idea of how this is supposed to work. So we'll talk a little bit more about this in class as well, but I wanted to give an introduction into the adjoint and the way we can use the adjoint to calculate an inverse of a matrix.